Hello, everyone. So it's a real pleasure to be here, and especially on this last day. I'm still amazed by the number of people that are still here after all this time. And I'm going to talk about federated learning and distributed machine learning. So just before starting this presentation, what I would like to know is who here, before coming to PyData, knew about NuBank? Okay. Who here, after like spending 3 days here, like know a bit more about NuBank? It's not too much. Okay, that's fine. And my last question is, I guess, like on the description it was written like distributed machine learning, but I guess here like the more central point is going to be like federated learning, and I guess it's kind of like a new field that appeared like 2-3 years ago, and I would like to know also like who here know about federated learning? Interesting. So at least you will, learn about something new today, and like when you will leave this room, you will be able like to maybe talk with your friend, with your colleague about this new field inside like machine learning. So first, I would like to just introduce myself. I'm Thierry. I'm working at NuBank for since like 2016, so more than 3 years and a half. I have like 2 master's degrees from France and from the US, where I did computer engineering and computer science. And then after that, I decided to continue with PhD in Germany, where I worked on recommendation system. And I always kind of put like factorization machine because sometimes there is just like one person in the room that heard about this algorithm and maybe like work on that, especially if you do like recommendation system. So I don't know, like if you are this person, like please come and say hi. I would love to talk with you. And otherwise, just before we start the presentation, it's also like just tell you like a bit more about NuBank. So NuBank is the leading financial technology company in Latin America. So if you don't count even like India and China just by like the sheer number, we're like the biggest fintech company in the world. And we launched like in 2014 like a no-fee credit card that you can just like manage on the app. We have more than 13 million customers. We are like this year expanding in Mexico and Argentina, so a bit like why we are here, and we're like giving some presentation because we would like to be a bit more known. That's like what I saw at the beginning of the presentation. And we were like elected like the most innovative company in Latin America, and I think on this point, just also like to go back a bit on like the presentation. We always try like to do innovative stuff. So we try to apply state-of-the-art method. We try to apply algorithms that we think are like really interesting and that can help our, let's say, like bottom line or the way we are either like treating our customer or doing business. And for that, a bit of what is like related to that. So in a way, federated learning is not something that we are using today at NuBank, but this is like kind of like a new method that we're like looking at, because as you can expect today, a big company like NuBank, or if we think about, let's say like Instagram, Spotify, Mercado Libre, we have like a lot of data, and most of this data is not generated on our side, but generated on like the side of the customer. So what we would like to do is to really focus on like multiple points. So usually when we talk about like decentralized data, we talk about trying to do most of the computation on the side of the customer. And usually when we talk about like on-device inference, for example, we talk about improving the latency, improving like the privacy, battery life of people, and like the fact that this can work offline. So in some way, for this presentation, I will mostly like focus on the privacy advantages. I'm mostly like focusing on that because like the field is really big, and in 30 minutes it's going to be really hard for me to just go through everything and being able to be like clear enough so at the end you don't like your head doesn't explode at the end. So I will mostly like care about like the privacy advantages here. So just to go back a bit, the field of like federated learning kind of like started with Google in 2015, where like the core idea was to solve a machine learning problem locally on user devices. And what is going to happen is everything that is happening in these user devices is going to be like aggregated and sent to like the server inside the company, but you will kind of like never see the data from the customer, only some update, and that I will explain later. So yeah, mostly that. So in some way, if we look at like distributive optimization for like machine learning, Again, what's going to happen is the data that we're going to optimize is distributed unevenly. So in some way, we have unbalanced data in the sense that some users are going to be more active than some other users. So some users are going to generate way more data than some other user. Over a large number of nodes. So again, here we're talking about massively distributed in the sense that we're going to use the cell phone directly, the smartphone of every user, to do some computation. This computation is not going to be really big, but it's still going to do some computation. And usually, what we are thinking is during this process, the training process is going to be much bigger than the average number of people that we have in our, let's say, context in the graph of all the users that we have. And yeah, we refer to that as federated optimization, where again we have a lot of non-IID data. And when I'm saying non-IID data is since the data that we're receiving is usually from just one client or multiple clients, but if we just look at one particular user, this data set is not going to be representative of the general distribution that we have when we, let's say, aggregate everything. And the last point that I didn't talk about is the limited communication. So on this point, again, what we're thinking is, when we're thinking about, let's say, Latin America, if you are, either in Brazil or in Argentina, most likely there is some part of the country where you have, no network. So it means that if you are relying on internet 100% of the time, well, it's really bad for you. So you want to be able to build something that's going to be work without internet, or at least internet connection that is sporadic. So once in a while, and again, doesn't necessitate to have a frequent connection to do that. So I'll go next to kind of an example. So if you know that is something that is called the glide typing from the Google keyboard. And in fact, what is impressive is not so much the glide typing, even if it's an amazing technology. But something that you might have seen at some point is just this piece of information. So every time you're typing a word, you see that just where there's the blue arrow, there is 3 recommendation of word that we might have after the sequence of character that we're typing. So in this example, I tried this morning of just typing PyData is a good, and then stop typing, and Google was just recommending me ID, time, or things. And the way it works is by using a recurrent neural net model that is distributed and on device, and that is using federated learning to do that. So kind of the goal and the example that we've seen until now. What we're trying to do is to be able to develop state-of-the-art machine learning. So in the case of the Google keyboard, it was a recurrent neural net. So we're not talking about really small model or really simplistic model. We're talking already kind of deep learning model. And what we're trying to do here is we're trying again to not every time send the data back to Google, because in some way, when you're doing communication with people, a lot of companies really value privacy. And if I'm not sure if everyone really care, or maybe not, but I don't want Google or Facebook to know what I'm talking about with my friend, with my girlfriend, or the people I work with. And that's something that's personal, and I really value the fact that everything is just staying on my phone, and we're not just sending a bunch of text to some big company that is doing some machine learning on top of that. And again, just to reinforce this idea is data is usually born not on the company server, but on the customer device. And we can talk about usually the private data. So maybe let's say you're doing some registration for some company. Today you have to maybe generate, well, the email, the company will need it maybe to send you some communication. But let's say if we talk about the age of someone, the race of someone, some, let's say more private information from a customer. This is the kind of data that a lot of companies are asking. And in the case of Nubank, for example, we have a really huge team of people in information security that is making sure that this data is protected. That if hacker is trying to get this data, is really hard for them, or almost impossible. And maybe here, what we want to do is is there like maybe a way to not like receive this data but still be able like to do machine learning? And I think if we are able like to do that, well, it will like remove a lot of anxiety that we might have in like getting all this data and storing it and making sure that this data is not available for, let's say, like bad people. So what do we need to do that? In a sense, it's really simple. There's kind of like a 3-steps process, but as you can imagine, usually like the devil is like in the details, and most of the time, like just one of those points is multiple paper written by, a lot of different researchers. So let's just try by the first, like the ML optimizer, and this one is kind of like the easiest one. As you can imagine, it's like gradient descent. And in fact, not like gradient descent, because as you can imagine, like if we have to do like pure gradient descent on like on a phone, usually gradient descent is like asking us to go through all the different data that we have and then like compute like the gradient at the end. And it's like too expensive in our case, because again, what we want to do is just send like updates as soon as we can have them, or as like some kind of like batches. So in this way, what we'll use is, well, stochastic gradient descent. And here, usually, it's like it works way better when we just have like a run of computation. It's usually like pretty low, like to compute. So there was like a nice paper that was like released not so long ago called like Distributed Machine Learning on Mobile Devices. And they did kind of like a survey of like multiple techniques for like machine learning optimizer. And here you can see like SGD, you can see like SVRG, which is like stochastic variance reduced gradient, Adam, Ogwal, ASGD for like asynchronous. And you see usually what is like the cost of using like those different, let's say, optimization method to do some optimization in some way. The second part is usually like the distributed optimizer. So in some way, if you kind of like think about it, it's a bit of doing like MapReduce. So we have like a really huge problem that we want to tackle, but what we have is a lot of like small worker, which is here in like the smartphone, doing the work for you. So what you're trying to do is, it's like really hard to train like a full model on a single mobile device, and you want to like divide this task in like all the different nodes that you had inside like the graph of like all your customer. And what's going to happen is like each of those workers are just going to deal with like a small specific problem. So in this case, just doing some optimization using gradient descent on like some of the data that you might have. And then after that, like we have some kind of like manager that is just going like to get everything together and like process it. So again, if we think about it, on mobile devices, the availability of like the network is something that is like sensitive. And if we think, like in terms of like distributed programming, the way that like Amazon is doing or Google is doing by just having like those really like gigantic server doing like a lot of computation, I think here like on the other case is it's like different. Like we don't have maybe like power every time. Like if your phone is like dropping down, you need to make sure that it's not like bringing like the whole network down. So this is something that you have like to get in mind. You need also like to reduce like the communication, because again, if you think that like the network is an issue, you might also think that in some part of the country, like people don't have like a 10 gigabyte like provider that is able like to stream Netflix, for example, and you have like to be really careful. So like the few information that you're going to send is going to be like really important. So you have like to be careful in like this amount of information that you have to send. So we have like this reduce of communication round. But also there is something that we call like communication compression, and maybe for some of you, you might have heard of this term, because there is like two ways of doing it. So there is one which we call like structured updates. So in like quickly, it's just like applying restriction to update during like the whole training process. And usually here is kind of, you have some result and you want to like reduce it by using, for example, like low rank compression or like some random mask. And otherwise, you have like sketch updates. So usually, like the compression here is done after you do the training and before the communication. So in this case, you have like subsampling, or maybe here people will know about like quantization. So instead of sending, let's say, like float number, you're just going to say, oh, like all the different weight of my model are going to be represented with just, let's say, like 8 bits. So you can like way reduce the amount of data that you're sending instead of sending 64 or 32 bits of information every time. And then the last point that is for me like the most important, because like the one from before, like the first point, as I said, is mostly like optimization. We all know, gradient descent. The second point is something that was also like done before in a way of like MapReduce, being able like to distribute like the computation to multiple nodes. And the last point is data aggregation. So as I said at the beginning, once the training is finished inside the device of someone, we need like this information to go back to like the server and to be able like to use this information to also update all the different nodes inside like the graph of all the customers that we have. So if we just apply like updates to the global model like one by one, it's going to get like really complicated, and usually one of the big issue that you will face is like the model can change like really quickly. The fact that again we have like an imbalance in terms of user, like some users are going to generate a lot of data when some other users are not going to generate a lot of data. So you might have like some issue on like overfitting, like instability inside like your model. And also, it can be like time consuming because again, like you're going to have a large number of updates to do. If like every time you receive an update from like one person, then you will like broadcast it to like the rest of the network, and then like the update of someone else and broadcast again. So what you want to do is that you kind of want to aggregate everything at once, so you're like saving time. So one way to do that, some interesting like fact, and that's something that will like come back to what I said at the beginning about me being like really interested in like privacy. So some of like the aggregation process that we have is what we consider like irreversible. So once you're like sending data in some way, you cannot really like inverse engineer like what happened, like what kind of information like change for like the customer. So in some way, it's really good because again, we're not like receiving any like private information from the customers, just update from like a model. And we can use different concepts like differential privacy to be able like to aggregate like those information in even more like secure way. So two example, and there is like way more than that. The first one is kind of like simple averaging. So let's say, I don't know, we have like logistic regression. You have all the parameters for like the logistic regression. And then using the data from like one device, you do like the update. You see that like the weight change for like this specific customer in some way. You like broadcast that to like the server. The server is going like to get like the update for like multiple different people, and then you're just going to do like the average of like all the update, like weight update that you get. And the second one is a bit more, let's say, like solid, which is called like federated averaging. And for federated averaging, like the base of it is what we call like common initialization. So common initialization is on each of the device of your customer, you're going to have like a model. So it's going to be like the same model. It's going like to be, like sometime get like the new weight from like your server, and then like update some of the weights that you have like internally. But the way you're going to, let's say, like send the model at the beginning, what you want to do is to make sure that like the initialization, so like the weight of like all your parameter for your model at the beginning is exactly like the same for like on each of the different devices. And we're doing that because if we don't, what's going to happen is we'll have like a really big performance loss. And there was like a simple experiment done on NIST. So NIST is the like image classification data set, where it's just some digit that you train like to classify from pictures. And this show that not having like the same initialization between like all the different model is making it like really hard to have like a model converging at the end, or not having like a huge drop in performance. And usually at the end, again, doing like the shared initialization for everything, the final average model that we get at the end has like a huge reduction in loss compared to like the whole data set. So I talk about like simple averaging, federated averaging, but we have like ensemble compression, co-distillation. Again, like the paper that is like did some kind of like survey is like showing you the difference in terms of like cost, speed, some issue if like your model has some like non-convexity, if you need like some additional space or asynchronous communication. And kind of like a new paper that was released also like from Google. Is something they call like secure aggregation. So maybe like for some of you, like everything that I said so far, you're saying, oh, we have like those, like update of parameter, and maybe, getting those updates is already like giving us like some information. Maybe, like saying that, oh, like race for like customers going up and down is maybe, going to tell us, oh, something is happening. So if you're like an attacker and you're getting like those weight, maybe you can do something about that. And one interesting way to avoid like this situation is what we call like secure aggregation. So secure aggregation, what it's going to do is you're going to encrypt every time the data that is going to be sent from the device to the server, and the server will only be able like to decrypt every like weight that you sent only after, let's say, like I don't know, like a number T of people contributed to like this computation. So let's say, I don't know, I'm sending you like information. We get like 30 people sending like this information at some point, and then once we arrive to like this threshold, and I will show you like a bit what is like the exchange happening between, let's say, like the devices and like the server, and we'll be able like to see that only when we arrive to this threshold, we'll be able like to decrypt the data, and then we'll be able like to do like the update on like the general model, and we'll be able like to send it back to every devices. So just like a quick picture. So on the left is kind of, like what is happening today. So let's say you are, like in a cloud host provider, so Google, Amazon, Microsoft, for example. And today what is happening is every interaction that you have on your mobile is going to, like generate some intelligence, and then it's going to generate some data that is going to be sent to like the cloud, and the cloud is going to, maybe update their model, update their like pre-trained model, for example, and then it's going like to send it back to your device. In the federated learning like mindset, what's happening is you have this part where the model is still like learning without having to leave like your device in some way, so it doesn't have like to go back to the cloud provider. It's already like learning directly inside like your smartphone. And then once in a while, as you can see on the right, you will have like this piece of information, this piece of knowledge that will be like aggregated, and then that will be condensated inside like just one piece of information, which will be like the new model with like the new weight, and that will be sent back to every devices. And in secure aggregation, what's going to happen is you have exactly like the same, let's say, like configuration, except that this aggregation that you will have in the middle is going to be like secure in a way of, cryptography. So like don't worry about that. Usually it's a lot of, generating like public key, sending like the public key to someone else, being able like to decrypt it, and you have like a lot of interaction between the user and the server. You're waiting for getting like enough user, and like the part that are in red, I think it's usually like what guarantees like the security of like the whole concept. So again, at this point, we only like learning stuff by using like the client inputs, and we are only able like to see that once it arrives in the server and once like being processed, and then we never store anything. And usually like the overhead is like pretty low, and we can tolerate like a large amount of like failing devices. So no matter like where the customer is, like it will still work, and we'll still be able like to update the model, because when you arrive, I guess, in a certain size, like million of customer, it's easy like to just have still like people generating data and being able like to give you like some information. So I hope that you're not too lost, and we can just like kind of like summarize everything with just this picture. So if we start by like the upper part in the middle, you have like all those devices that started with a single model, and then we'll go like to A, where like a user is going to interact with me, like maybe the application, and is going like to change the state of like the model that he has inside his application. So it will go from like just having this blue circle to like a green square, and then we'll not get like this update just for like one device, but for every possible devices that we have. And then everything will be aggregated and will like be transformed to like this losange. I'm not sure if it's the word in English. And once it's like processed, will be like back in C, and like this new model is going to be sent and broadcast to like all the different devices that we have. So luckily, I didn't use like any like formula, But we are like in PyData, so, well, I need to put some code. Fortunately, like, if you don't want to, like, go and read thousands of paper about like implementation details, TensorFlow released TensorFlow Federated, and they have like tutorial for a couple of data sets where you can already get a sense of what's happening, what do you need to use, how do you write like the code to do that. So in this example, this is like what we have, but you will see that if you go on the website, it's way more complicated than that. It's still like kind of like work in progress, so a lot of stuff is changing. There is a lot of like improvement, but as you can see, there is like really few imports. We load like the simulation data, so it's some kind of like a version of like MNIST, again like the computer vision like image classification. And then once you have these data sets, you pick a subset of clients. So in this case, we just pick like 3 fake like customer. So we just like create like a list. It's really simple. Then you show like TensorFlow Federated, like how your data structure is going to be like. And then once you're done, you just like declare like a model. So in this case, we're using a Keras model. And we're just using a really simple one, so it's like a dense layer. There is like 10 different classes. We're using like softmax because we want to predict like just one classes. And the input shape, like 784, is mostly because we are dealing with like 28 by 28 pictures. Then you compile the model. We use like constant entropy. We use stochastic gradient descent with like a like an optimizer around like 0.1, maybe like a Gaussian, I guess. And once you're done with that, then we can just like simulate what will happen if we're doing really like federated average processing. So we'll just like run the model. In this case, we're going like to run it for like 5 iterations. And if you look at the results, you will see that like the loss is decreasing, no matter like who's going like to communicate with you. And in some ways, it's working. But again, like disclaimer, it's way more complicated than that. If you go on the web page, like there is like this like really small snippet, but like if you go in more details, there is like full paragraph every time for each of like the line that they have to really explain details like what's happening. And if you're like really interested, there is another website called Leaf that is done by Carnegie Mellon University. And here you have, I'll just list like 4 of data set, but there is I think a bit more. There's like another one again from MNIST. One from like sentiment analysis, another one for character prediction, and one to just like create synthetic data sets. And what you will see here, and that is like interesting, is for each of those, you see like the number of users, because this is like the way like it should work. We're not talking about just getting like data, and we don't know like from where this data is coming. We still want to know, like in a real case, where this data is coming from. If we can, like have like some small batches, so we can like replicate what will happen if you have something that is really in production. So there's like a lot of different resources, and otherwise, thank you.
¿Alguien tiene preguntas?
Are you applying any of this on your work?
So today we are mostly like looking at it because, again, as I said at the beginning, we are like interested in like being able to do like state of the art, being able like to like also like respect like the privacy of our user. I think like the idea is maybe soon like in a hackathon to be able like to demonstrate if this is working, this is something that we can like replicate with, let's say, like real data. But so far no, it's like nothing yet. Like we're like really far from anything in production, for example.
Okay, thank you for the presentation. So my question is, you said there is little overhead. So did you measure that? Did you, does the client notice any lag, anything? So you said there is little overhead. So any measure on that?
For the overhead?
Yeah.
Okay, so in terms of like overhead, again, if you think, let's say, I don't know, like logistic regression, let's say you have like 10 parameters, and let's say you use something like quantization. what you're going to say is you can just send 10 times 8 bits of information back that is going to just say what is the value of each of those parameters. So in terms of again overhead, it's less than sending I don't know maybe a full word or a sentence to your friend. So it's again really small compared to different method or full-blown data where you need to send all the data back to the server. It's going to be way more expensive to do that, and just send updates from a model.
Here. Thank you for your presentations. Actually, I have worked with this topic in my thesis projects, and the two pitfalls that I had was one, the conversions, and then the two, the efficiency, because you don't have warranties. At least in my schema, I didn't have warranties of the conversions and the efficiency. Regarding the efficiency, when you are aggregating all the models and in order to calculate the updates, you are waiting for all the models to be trained in order to have the update. So how did you deal with that?
I think here, yeah, it's a really good question. Maybe I kind of forgot to tell that at the beginning. I think this method is not the perfect solution for everything. I think it will be really useful for again maybe models that are dealing with really sensitive information. If you're doing trying to predict I don't know, forecasting bike consumption in a city, please don't use that. It's overkill. But it's, if you're dealing with, let's say, private information, maybe geolocation of user, that's something that you don't want to have, those gigantic data set of people with information of where they are, and you're saying, okay, well, today, this stuff is being breached. I'm really in big trouble because this is really sensitive. So I think in this case is I wouldn't recommend everyone to switch all their model to use that, and especially in the fact that some of the limitation, as you say, is the aggregation. There is not everything that you can say express in terms of aggregating the weight at the end, and even in some of the example that they have, it's mostly let's say some texts, so image classification. If we think more in terms of, let's say, maybe tabular data, maybe it's something that is not as powerful as just doing it by yourself instead of doing it on the side of the devices of someone.
Thank you.
¿Alguno más?
Hello. You talk about spectral gradient. What is better for you, spectral gradient or maximum descent or descent by gradient?
So
Yes or not?
So the different optimization that I showed at some point?
Yes, what prefer you?
I think, for, if you just want to do a prototype, I think the optimization way to go is stochastic gradient descent, because the easiest one to implement. There is nothing fancy to it. There is other stuff like Hogwild, Adam. There's just a small let's say changes to your formula that you need to optimize. But again, I would say just go for stochastic gradient descent, because it's already something that is quite complicated to use. If you start from the start doing something really fancy just for the fun of it, it's going to be really complicated for debugging at the end. So just try it the easier way and go for that.